Hello and welcome back to episode 10 of Polynomials. Today we're going to be looking at quintics and beyond. So first of all, we've had a formula for all the previous polynomials. We had one for the quadratic, we had one for the cubic, and one for the quartic. No such formula exists for the quintic because it is unsolvable by radicals. What that means is you can't lay out a formula in terms of the 5 basic operations, plus, minus, divide, multiply, and nth root. You can't lay out a formula in terms of the coefficients and these 5 operations that will lead you directly to the answer. You might get close, but you won't actually be able to get there. What Galois, who was a French mathematician in the 1700s, what he said, he created something called Galois theory. And he said that if something's Galois group, I'm just going to write down his name, if something's Galois group is unsolvable, then it is unsolvable by radicals. And so for the quartic and below, their Galois groups are solvable. But for the quintic, part of it is solvable, but part of it isn't. So for example, let's say you had an equation x to the n minus m equals 0. That group is always solvable, because you can just say that x to the n is equal to m, and therefore x is equal to the nth root of m times zeta. Have I drawn that correctly? I think that's a zeta. Times this special symbol to the p, where p is great. That's not a p. Where p is greater than or equal to 0 and less than or equal to n. And zeta is just an nth root of unity. So what that really means is that if you were to represent this on an Argand diagram, you would get, so for example, the square root of 1. So root of unity means root of 1. So the square root of unity, the square root of 1 would be represented as 1 here and 1 here. Cube root would be 1 here, 1 here, and 1 here. And the quartic one would have 1 in all these 4 places, and so on. And so that's what zeta represents. So this particular group is solvable. But the point is that not all quintics are solvable, and therefore we can't represent them by a formula. The proof of this was done by Abel and Ruffini, and therefore it's called the Abel-Ruffini Theorem. So if you want to look more into that, I will link some resources that you can look into below. Now I realise that would be quite a disappointing point to end the video on, so what I am going to do is I'm going to show you how to solve a quintic that is solvable, and how you can just solve that, not using a formula, but by intuition and problem solving. I got this problem from a channel called blackpenredpen, so if it seems unoriginal, that's because it is, and I am going to show you how to find the solution to it. So we have x to the 5 plus x to the 4 plus 1 equals 0. Now, looking at that, you can't see some way to instantly factorise it. So what we're going to do, as we do in many areas of maths, is we're going to try and simplify it and then bring it back to where it is right now. So first of all, it would be much more simple if we had all the other terms. So x to the 5 plus x to the 4 plus x to the 3 plus x to the 2 plus x plus 1 equals 0. or it doesn't equal 0 because we know that this expression here equals 0. So the way we're going to factorise this is we can take a factor of x squared or x cubed out of these three terms. So we take x cubed, and that will give us x squared plus x plus 1 plus x squared plus x plus 1. Now you'll notice that what's left is the same as what's in the bracket of the x cubed. So what we can say is that this will factorise to x cubed plus 1 x squared plus x plus 1. Now, how does that help us with our original problem? Well, all we're going to do is we can write our original problem by saying that x to the 5 plus x to the 4 plus 1 is the same as writing x cubed plus 1 times x squared plus x plus 1, which is what we found up here. But this time we're going to minus x cubed minus x squared minus x. And what that will allow us to write is that will say x cubed plus 1 times x squared plus x plus 1 minus x times x squared plus x plus 1. And that can then therefore factorise to x cubed minus x plus 1 times x squared plus x plus 1. Now we can solve this because we know that that is equal to 0. So first of all, we know that x squared plus x plus 1 equal to 0 has no real roots. And the way we can simply check this is b squared minus 4ac in this context is just 1 minus 4, which is minus 3, which is less than 0, and therefore it produces no real roots. So the next thing we can look at is that the other bracket must produce our real solution, so this bracket here. So we can write that x cubed minus x plus 1 equals 0, and so we're going to try and solve that, and that will give us our real solutions. So first of all, how many real solutions are we going to get? Because we know we're going to get none from the quadratic. How many real solutions are we going to get from this cubic? So first, we have a negative p-value, and that gives us 1, 2, or 3 solutions. It sometimes helps to know the p-value, but in this case it hasn't really helped. It's just told us it could be anything from 1 to 3. What we're now going to look at is the discriminant. So we know that q is 1 and p is just minus 1. So therefore we can say that q over 2 squared plus p over 3 cubed is just going to be 1 over 4 minus 1 over 27, because we know that minus 1 cubed will just be minus 1, and 1 squared will just be 1. And this number here, we have here, is going to be positive. So we know we'll only get one real solution. Well, that's good. So what we're going to do now is we're going to plug this into our cubic formula. Well, good thing it comes in here. So we're going to use the cubic formula. So we write that x is equal to the cube root plus another cube root sign. Cube root of negative q over 2, so q was positive 1, so minus a half plus the square root of 1/4 minus 1 over 27, which we found up here. And then we're going to write the same thing in the other bracket, just with a minus sign here. Square root of 1 over 4 and minus 1 over 27. And I can tell you that that will equal roughly minus 1.327. 3247? I think that's it. And that's our answer. So thank you for attending episode 10, and I look forward to seeing you all in my conclusion video of this series.